Welcome to this video on the Bronsted-Lowry model of acid-base reactions. We're asking a really fundamental question here, which is what is an acid? This has been a question that's perplexed people ever since acids were discovered, given the name acid because from acidus in Latin, which means sour. And then big progress made in the 19th century, understanding that acids had something to do with hydrogen, culminating in 1884 when Svante Arrhenius came up with his definition of an acid as some molecule that contains H+ ions in solution. Today we're going to just slightly go to an extension of Arrhenius's ideas into what's called the Bronsted-Lowry acid base model. This was independently come up with from two scientists, Johannes Bronsted, who is Danish, and Thomas Lowry, who is English, working around 1923. And it's very much the current theory of acid reactions today, along with a related theory by Gilbert Lewis that he came up with at a similar time. But this is current cutting-edge acid theory. So let's try and go into understanding this model. Now, before we do that, I just want to give you a little bit of a thought experiment to think about ethanoic acid. So ethanoic acid is this molecule here. It's going to dissociate in aqueous solution to form H+ and CH3COO- ions. Now, one way you can try and understand the concentrations of these ions is to use a conductivity experiment. So the way that works is you take a beaker and you put your ethanoic acid solution in here. And you're then going to take some kind of cell here, and you're going to connect that up to some sort of electrode, inert electrodes, so maybe graphite. And then in series with that, you're probably going to put some kind of bulb or perhaps an ammeter. And then you've got another electrode here. In fact, let's make it an ammeter. So you'd expect, because we've got charged particles here, that the H+ ions that are in here are going to move towards the negative electrode, and the ethanoate ions here are going to move towards the positive electrode, and that's going to make a completed circuit. Now, the question for you to have a think about here is how will the conductivity of that solution vary as its concentration gets higher? If I use exactly the same electrode positioning and I look at the current flowing on that ammeter, will I get more current when I have a higher concentration of ethanoic acid or less current? Have a think. Well, here are the results. What we actually see happening in this experiment is that the conductivity actually drops. This is essentially like the concentration. So the higher the concentration of ethanoic acid, this is conductivity. The lower the conductivity. Now that should surprise you. Over here we've got less ethanoic acid, so it stands to reason that you should have fewer of these ions. Here we've got lots and lots of ethanoic acid. Surely that means we've got more of these ions. But the answer is actually quite the opposite. Over here we've got a lower concentration of H+ and concentration of CH3COO- ions. Here we've actually got a higher concentration of H+ and CH3COO-. How can it be? Why are these results the way they are? Well, what we need to understand here is that actually this equation here is an oversimplification. We're going to use these types of equations in this topic a lot, but it's actually an oversimplification for fundamentally what is going on, because actually the water is fundamental to what is going on in this situation. Water is active in dissociation. Let me show you that by means of a mechanism here. What's going to happen here with this water molecule is the following. Just set that up, drawing the water molecule properly. Now, because of the polarity of these bonds, this oxygen is going to be delta minus, and these hydrogens are going to be delta plus. Now what that means is that this oxygen is sucking the electrons in this bond towards itself and leaving the hydrogen without enough electrons. Now this oxygen atom here has actually got two lone pairs on it, and one of them is going to be, because it's negative, attracted to the hydrogen, and eventually this lone pair is actually given to the hydrogen, which was what we call electron deficient, lacking in electrons. Now the hydrogen can only form one bond, and so this bond is going to break and the electrons are going to be stored on that oxygen. So what we've got happening here is the loss of H+. Now because an H+ ion is essentially just one proton, this is known as deprotonation. Deprotonation. We've lost a proton. And I'm just going to give us a slightly longer arrow here. Okay, now if we draw the products of this reaction, wary of space, but hopefully it's going to be enough, we end up with the oxygen here having a negative charge sat on it, and an extra pair of electrons that it was just given from that bond. And now we have the water molecule has become the following. We've actually got 3 hydrogens attached. This hydrogen here, if we were to just do a little bit of highlighting, this hydrogen here is actually this one here. Of course it's indistinguishable. And we've ended up with a positive charge on this because this lone pair has been given to form that bond. It's essentially lost 1 electron more than a fair share for a normal covalent bond. We've got a dative covalent bond here that's been formed, and so we've actually got a positive charge here. Okay, now this situation, what is actually going on here? Well, water is removing an H+ ion, and that is what Bronsted-Lowry said was acting as a base. So water is acting as a base. In the Bronsted-Lowry model, a base is a proton, or should we remember proton is H+, acceptor. In other words, it bonds to proton, i.e. bonds to H+. That's a base. Now, this molecule here is acting as an acid. Just to be consistent with later on, I'm going to use this. So this is a base. Water acting as a base. This is acting as an acid. An acid here is a proton donor. And donor is just simply a way of saying, i.e. it loses H+. So this was our original model of dissociation, which is that you put ethanoic acid into water and it just H+ just drops off. Now we see here that this is not actually what's going on. What's going on is the water is acting as a base and actually removing or accepting a proton from the acid. And this reaction is actually reversible, as is indicated here. So you can have ethanoic acid reacting with water to make these products here. But that can just go back the other way, because we've got a positive charge there. These hydrogens are still having electrons sucked away from them, and it might be the purple one, or it could be any of the others. I'm going to make it the purple one just for the sake of argument. This lone pair of electrons can come back here and pinch off that proton again, and this can go back the other way. So this is actually a reversible reaction. Now that is interesting. So we said earlier that water is a base and ethanoic acid is an acid. But they're not the only acids and bases around, because if we think about what this molecule here is doing, it's actually taking a proton off this ion here. And so we have another base. This is actually a base. Now, in order to try and distinguish these two, we'd probably give them numbers. So this one we call base 2, this one we call base 1. Those labels are arbitrary. Now this molecule here is another acid because it's being a proton donor. It's having this proton removed, so this is another acid. We're going to have to call that acid 2. Actually, we're not. I'll come back to that in a second. So this one here is an acid. Now, let's just think about finally the labeling. So these guys here are both bases. We're going to give them labels 1 and 2. But what we want to try and do with these labels is to say, okay, well, base 1, actually, when it gained its proton, it became this. So the right label is to call this acid 1 because these guys here are linked. And they're known as a conjugate acid base pair. They are interconverted by loss and gain of an H plus ion. That's the only difference between H2O and H3O plus. So these guys are called conjugate. Conjugare in Latin means to join. You talk about conjugate union is all about marital union. So this pair are an acid-base pair, and so we give them both number 1, and then this guy here is actually the conjugate base of this acid here. So if we're going to draw another set of arrows, we're going to say these guys are also a conjugate acid-base pair. And so you can talk about this as being an acid and this as being its conjugate base. I won't write the whole thing, but conjugate base, and this one here would be the conjugate acid of this base here. Now we could equally have called this base and this conjugate acid. It doesn't actually matter. Typically the ones on the left hand side of the equation are called acid and base, and these ones over here would be the conjugate base and the conjugate acid. So that's the fundamentals of the Bronsted-Lowry theory. Acids and bases always come in pairs. Now, final slide just to have a look at here. This is ethanoic acid for you. So the pale grey water molecules in the background here are a solvent for the ethanoic acid, but they also act as a base. You see here, we've got the base, that's water. And they do so by removing this H plus from the HA molecules. So here are the HA molecules. These are the dark grey ones of the ethanoic acids. And you can see in some cases that this little H here, H plus, has been removed and they have become A minus, which is the ethanoate ion in that case. It hasn't happened to all the molecules because this is a weak acid. And in so doing, that proton has actually been transferred onto a water molecule and it's become this ion here, which is known as H3O plus, is known as a hydronium ion. Oops. Now, the thing that's different here is that there is no H plus here, or at least no free H plus ions. A proton is way too unstable to exist by itself. If a proton were formed, it would quickly be snapped up by an H2O molecule because those lone pair of electrons there will be immediately donated to it. There's no free H plus. So when we talk about acid in solution, it's this. This is H plus aqueous. Now there's all sorts of funky stuff happening with these guys associating with each other in crazy ways, but H2O plus fundamentally is a better model of H plus aqueous. Now we're still going to use H plus aqueous a lot in our equations because it's a simplification, but from now on you've got to understand that actually that's a hydronium ion, and you can write equations like this. In fact, that's a more full way of writing it. So this is what you've been writing up to now as H plus aqueous, and that's the Bronsted-Lowry model of acids and bases.